Transition. Next up is Tomás from Carnegie Mellon, who will be talking about finding needles in haystacks and some lessons learned from observation run for.
So my name is Tomás. I'm from Carnegie Mellon. I work with Antonello Palmese, and for the last 3 years, I've been chasing black holes and other gravitational wave events with the dark energy camera. And the pitch to me was, again, kind of what kind of compute bottlenecks do we run into, but then also what does it look like kind of in the trenches when you're doing gravitational wave follow-up. So I'm at a point where I feel like my talk is going to be very abstract, going over and very human in a lot of ways about what do we actually deal with. And one big contrast that you'll see in a few slides is that we are not Rubin, we are not LHC, we are not this big international collaboration of tens if not hundreds of scientists. We are a team of 7 scientists, and we're trying to answer a lot of the same problems, and that naturally comes with not just computational bottlenecks, but a lot more time, just the human and the funding bottlenecks we run into. So the outline of the talk is I'll go over background and kind of things and the kind of things we're looking for very briefly. Then I'll walk through what does a follow-up look for us, kind of in the day-to-day, and then at least the lessons that I'm walking away from that, some of which have already been stated during the conference, but at least the ones that I would like to emphasize. So we had a wonderful talk by Michael Coughlin yesterday about binary neutron star mergers, where you have these 2 big balls of neutrons, they're swirling around each other, smashed together. That creates a big explosion that we call a kilonova. We've successfully found the kilonova for a binary neutron star merger once in 2017. And so this is what a lot of the field has been behind we're looking for the next one. One problem is that these things are very rare. And so but then the other kind of gravitational wave event that we have is a binary black hole merger, which occurs with about 100 times the frequency. And while black holes themselves, we don't necessarily expect to produce an observable signature. If we have 2 black holes that merge in an environment of a bunch of gas and dust, like in the center of a galaxy, which is also, there's also some theory there that those kinds of environments can accelerate the formation of these binary systems through dynamical friction, and by the deep potential well trapping heavier black holes. That if these black holes merge in a bunch of gas and dust, they could also produce a flare that we can observe. And there's been no confirmed flare, but over the last decade or so, there's been a growing number of possible flares. That the principle is that if you build a big enough population of these flares, you can then do the statistics, figure out, maybe if you can't figure out which one of those are actually counterparts or not, you can figure out how many of those are counterparts. And that can be very important to figure out where these black holes are merging, because as you've seen before, we have these big bananas in LIGO, and it's very hard to pinpoint exactly where this thing is coming from. So that's the gist of the science, and now this is the team that we're working with. All of us are based at Carnegie Mellon, except for Igor, the co-PI. And then we have many other, and so this is the main DCAM team that we use the dark energy camera to look for these things. And then we have a lot of other collaborators who are helping out on the theory side, helping out with other facilities like ZTF and whatnot. So this is who we're working with here. I've already gone, or there have been other examples of kind of consideration that you go through when you do a follow-up. But we first have to receive the trigger. LIGO tells us what they saw. We decide whether it's something worth going after. We decide where we're pointing our telescope. Then we actually take the pictures. We process the pictures. Then we don't just, as was mentioned yesterday, we don't just think about the new data that we collect. We also want to look at old data. And so we have to collect that all into one place that we can see all of that together. And then we actually have to look at all those data and decide whether this was actually something that we think is the genuine counterpart or not. And So I'm going to touch on most of these and in a little bit more detail in the next few slides. But the main gist of it is that the absolute ideal would be if we can close this loop between taking data and then figuring out whether there's something in our data every time we take an exposure. Which for DCAM, it's however long it takes to take your picture, and then plus 30 seconds for the readout. And that's the cadence that what you're getting new exposures. And so, spoiler alert, we're at the point where we can get the measurements out of the images well under this time. However, a lot of the other things about cross-matching with other data sets and with actually putting it in a format that you as a person can process in this cadence, that's the hard part for this. So again, we have these LIGO bananas that they announce via the public alert stream, and we get this sent into a Slack bot. Vedshaw, who gave a great talk yesterday, a few years ago, put the work into building the bones of this, and then we expanded on that to run some additional analyses. So this is our wake-up call whenever something goes boom in space. This is what lets us know that's happening. Then some of our considerations that isn't a huge computational challenge, but is still interesting to think about is how do we decide that something is worth going after? One of them is, do we have archival coverage? Can we immediately do the image subtraction that other people have mentioned to see if there's anything new in our images? The event parameters. So here, is it a black hole event? Is it a neutron star event? Recently, LIGO's given us the masses, which is incredibly helpful. Thank you for doing that. Because the masses are very important for binary black hole mergers for determining whether we expect them to be in an AGN or not. Your usual astronomy is this thing on the right side of space that that's not behind the sun. And then, of course, weather. Are you clouded out? Is the dome frozen over? All that. So then going into planning the observations, this is again something that doesn't take a huge amount of compute resources, but still needs to be pieced together in some way. It's looking again, what have we observed previously? What kind of coverage can we do in the different filters? Do we have to choose particular filters because other ones we don't have coverage in? I put together this package that's a very VW Beetle-esque one, not a lot of knobs to twiddle, just kind of putters along, does the job. But Michael Coughlin has also led over several years putting together GW-MMADS, which is kind of your spaceship of doing this. There's a lot of knobs to twiddle. If you can punch in multiple telescopes, you can give it how much time you have on sky, and it'll figure that all out for you. So a few different tools there. So then the bulk of what I've been working on over the last few years is putting together the pipeline for this, because unlike a lot of large collaborations, we do not have years to put this together. We do not have a huge amount of funding to put this together. It was me and our postdoc that was really trying to get this off the ground. And so one of the big things why we created a more bespoke solution is that our postdoc put together an image differencing code SFFT that is GPU enabled and is much faster than the historical ones. And this is what really this is one of the big things that lets us get the speed we have in our pipeline. And so we have a few examples of our stamps here. On the left is the reference, in the middle is our new image, and on the right you see the difference image, which you can see the existence of different transients in those. That even in the case of large galaxies, sometimes you get little artifacts at the centers of the galaxies, but most of the time you get a fairly clean subtraction. I'm also realized that one thing I should have done is included an example of a nuclear transient where it shows the galaxy being subtracted out very cleanly, and you can see in the middle that we still have some existing flux, because that's not shown the best here with the dipole artifacts you have there. So this lets us altogether gets us to the cadence about 50 seconds per decam exposure, which if we take an exposure time of like 90 seconds usually, 90 plus 30 is going to give us 120. And so this alone is under half the budget we have for actually processing the images in the cadence we need to. So that's great because this is not a bottleneck that we have right now. And then after we do that, this is where I was talking about compiling with other data sets and then generate the summary plots, which this is the thing that I click through when I look for counterparts. There's about 2,000 to 3,000 of these every time we take a new set of data. You click through, you look at the light curves and try to figure out it's a good one. And that's getting into how we're assessing the data set. So our summary plots have the photometry. How does the brightness of the thing vary with time, with different filters? We can take looks at the stamps, see if we trust the subtraction, and then the data that we cross-match from the other catalogs here, we just included in this little text here, just host info. Is the host a galaxy? Do we have any redshift information of how far away it is? How does that compare with LIGO and all that? And even this kind of mess of a plot doesn't give us much of the context that we need, because a lot of the other things we think about is if there's a point, so like the green point here in the second to last epoch, that one's a little bit brighter than the redder filters in there. And so I might want to take a look at the stamp for that one, for that point, and see, is that a subtraction I trust? Is there an artifact? And so I can't do that very quickly without digging up the files there. Multi-band photometry, which here I mean not so much multi-optical bands, but do we have any X-ray photometry for this? Do we have any radio data or infrared data? And how does that look? Because that can be informative. What spectra are available? So there's archival spectra that exist through many of the surveys in the past, and then also if we take any spectra ourselves, we want to be able to compare this. And then similar to the archival question, does the host show any inherent variability that might be that might explain a transient we find more so than it being a novel event? And so there been some slides that in other presentations about different solutions to this. Sky Portal's one of them, where it's this kind of dashboard of transient science where you can scroll through, you can see a lot of this all together. And we've used Sky Portal, but there is a startup cost to getting that set up. And with only so many people, you may not have the time for that. So then in summary, what we did throughout all of 04 is we did 15 wild field follow-ups, which are all pictured here. Spoiler alert, we didn't find anything promising, but hopefully by the end of the year, I'll have out a summary paper kind of documenting what we did do, what are most promising candidates, and then some statistics on how much one we would believe that or not. And then we have several other special, more focused papers on events that were particularly interesting for that. Good. So that's kind of the summary of what we've been doing. And so then I'm just going to finish up with my takeaways from the last several years and kind of what to think about for the future. So now this next slide is going to be the most inflammatory one of the talk. But based on waiting for so long, based on that we've waited for so long for another binary neutron star event, that we've had plenty of black holes, that for IR1, that special LIGO run that's going to start at the end of the year, we really need to think about triggering on a binary black hole. Because we don't get a binary neutron star rate that doesn't include 0 until O5b. And so at that point, we might need to think about some other sources to look at. Excellent. Cool. So, so we are not operating on the scale of Rubin, where we're dealing with petabytes of data. One DKIM exposure is 300 megabytes, and we have about 100 terabytes on disk, which is still a chunk, but not too obscene. And so my proposal is that gravitational or real-time gravitational wave follow-up is not compute limited, but the hard part is that someone still needs to herd the cats. And in the presence of small teams where you're already stretched pretty thin, this can be a huge bottleneck. There are many points where Layer I had to be doing hot fixes to the pipeline throughout the whole time, and the science that we were doing at the end of 04 was fairly different from the science we were doing at the beginning because of all the things we learned. Another point is that only a human can say eureka, that in an age with many of the tools that we have that accelerate a lot of this, and the bottom line, there still needs to be someone who looks at the picture and says, we found something. And so the principle here is that what's been mentioned before, how can we learn to drink from the fire hose of all that is going through? And how can we really learn to synthesize all of this information that we have into something that one or a few brains can process? There are a lot of wonderful tools out there, but in science, there will always be scientists that want or require bespoke solutions to their problems. So this is a point, in some ways, more for the scientists in the room, is how can we make sure that what we're designing is modular, and that we're really using the best practices that we can, so that our code is just relegated to a corner of GitHub for the next however many years. And then the last point is that even at R1 institutions like Carnegie Mellon, there will be small teams doing important science and that do not have the resources of many of the large collaborations. And so while it's great that there are so many, that a lot of you are doing some great work on some excellent computational tools, that they still need to be accessible for people who don't necessarily have the time to learn all the bells and whistles of something. And so I'd be very excited to keep talking with all of you about a lot of things that you have available. And that would be how I sum up what I've learned the last few years. Thank you.
Okay, questions?
Yeah. So what telescopes data you use for this, or like what wavelength range? Like,
Yeah, so we work with the dark energy camera, so we work in the optical band.
and do you aware of this GCN circulars? GCN circulars. Like, so there is like a, for each gravitational wave, people also look for GRBs for other optical, and then they send alerts as well. Like there is gravitational wave alerts, but there is also like other observatory that also give alerts at the same time as these gravitational waves. Are you aware of that or no?
Yeah. No, we follow the GCN alerts of other observatories. We've been following a lot of that. We've collaborated with them. Several of the papers that I mentioned are in collaboration with ZTF and Wendelstein, other facilities.
Okay, thank you.
Hi, I'm just curious, when you detect transients or possible transients from AGN, are they like jets or something that break out of the medium, or do they just interact with the AGN and cause like different glowing spots or something like that?
Yeah. So one of the problems for the binary black hole case is we don't know. There is theory that there's jets. There's theory that there's this bubble that slowly forms as the remnant is moving through the disk, and then the bubble kind of pops outside of the disk, and you get an outburst like that. but there's still a lot of questions on the timescales, the colors, the brightnesses of that.
Thank you.
So how many, I guess my question is, how many other small teams do you think are out there like you? And is there a benefit in connecting with them as a solution to this, we're small, we don't have a big team? Like what, I mean, you sort of have this on the slide, but what solutions, or even how could information be communicated, docs, tutorials, recipes, FAQs, so that if you are trying to skill up in a small group, you can do so quickly and tell right away if this is going to solve my problem or not, or things like that. So those maybe your opinion on those two questions.
Yeah, no, I think that's one of the hardest questions about this. It's how do you, and in science in general, just how do you get the information to the right people? And I think it's workshops like this. I think it's those of us who are introverts fighting our natural urge to talk to people. Yeah, I mean that we were, one thing that I didn't mention that I should have is that we operate with is that we run our systems on a machine operated by Pittsburgh Supercomputing Center. And so a few years ago they offered trainings, but they don't anymore. And it seems that it's just, there's a lot of human limits in this. So.
Okay, let's thank Tomás again.